Hello, this is Professor Kuehn. Welcome back to my lectures on electricity, magnetism, and light. We have begun looking back at Newton, his book called Opticks. You might remember what we've done in the past couple of weeks is we've been looking at Huygens' wave theory of light, and now we're looking back at Newton, who is a strong opponent of Huygens' wave theory of light, as we're going to see as we discuss this chapter. Newton is going to argue that light behaves as a particle rather than as a wave. So, last time, specifically, we began into chapter 18 in a student's guide through the grade physics text. This is on page about 209 in a student's guide, volume 3. And to remind you where we were, is we were talking about Newton's study of birefringence. And so in figure 18.1 is depicted one of these pieces of Iceland spar or Iceland crystal. It's a kind of a parallel pipe head that is has a kind of a funny angle to it, and if a ray of light comes into it along line ST, it will break into two beams, one that obeys the ordinary law of refraction along line TV, and the other one that does not obey the ordinary law of refraction, that goes along line TX. So Newton calls the one that obeys an ordinary law of refraction the ordinary beam, appropriately, and the other one the extraordinary beam. Now, it's important to recognize that he's not merely interested in this as a curiosity, but he believes that it provides evidence for his particle theory of light. And specifically, you might recall that he says the only way that this could divide this initial ray ST into two separate rays is if there is some feature or some property that the light ray had as it impinged upon this crystal that the crystal could then select based upon in order to decide if it was going into ray TV or into ray TX. I think I used the example of if a shepherd's going to be dividing between sheep and goats to make two columns of animals, one needs to actually have two different kinds of animals that the shepherd could divide between. So what Newton is going to argue, and he did argue, is that we'll see this more clearly later on in the chapter, is that this ray ST that looks like a simple beam of light is actually comprised of a stream of particles. And he argues that these particles have sides, so to speak. So you might think of them, he doesn't say it quite like this, but this is how I think about it. You might think of it as these particles are little ellipsoids that have two different sides to them. And so if they're flying in a particular direction, if you have a gas of these particles or a group of these particles, some being oriented vertically and some being oriented more or less horizontally, as they hit this crystal of Iceland spar, somehow this crystal is able to determine the orientation of these and to divide them into two separate rays or two separate beams, one that acts in the ordinary way and one that acts in the extraordinary way. How the Iceland spar does this, well, that's not quite clear, but there must be some kind of, he says, some original modification is what he calls it, or original feature of these, so that some of them, let's say the ones that are oriented more or less vertically, go through in this and are bent this way, and the ones that are oriented more or less horizontally go through in this direction. That's the basic idea that he has here. And this is something that he talks about on page 213. I'm sorry, on page 200 and maybe it's about 211, 212. This is in his query number 26. He says, have not the rays of light several sides endued with several original properties? And that's where he explains why he thinks that these original properties, kind of the sidedness of these light particles, can account for these two separate beams. If we move on to page 213, he develops this idea a bit more. He says, well, what if we were to take this ray of light, this is an incoming light ray, which in reality, according to Newton, consists of this stream of particles of these kind of various orientations. What if we were to take this, pass it through a crystal, break it or filter it into these two different orientations, and then each of these we were to pass through another crystal? So let me draw this schematically like this. And I'm going to draw a vertical line on this crystal. Maybe I'll make it in a different color to emphasize this. Let's suppose this crystal is oriented in a certain way. I'm not paying attention, by the way, to the exact shape of the crystal. I'm just arguing that there's some orientation to this crystal. so that if this original ray of light was coming in with these particles in various orientations, that they would be divided into ones that were oriented, let's say, horizontally, and ones that were oriented vertically, so to speak. So here's the incoming ray, here's this outgoing ray, here's another outgoing ray. And let's call this one over here the ordinary ray, and this one the extraordinary ray. Well, now he says, what if we take another crystal, like this, I'm paraphrasing what he's doing, and we orient it in the exact same direction with respect to the crystal axes. You might think about the symmetry, the shape of this crystal, there's some kind of symmetry to it. We orient it in exactly the same way. So if this one was oriented, we'll call this 0 degrees straight up and down. This one also is oriented straight up and down 0 degrees. What's going to happen? Well, the ray coming through here will behave just like the one that was coming in. So it's going to act just like the ordinary ray. But what if we were to take this beam right here and we were to orient the crystal kind of at a 45-degree angle? This is what he talks about on page 213. So imagine orienting this in a slightly different direction. So this is at a 45-degree angle compared to the orientation of the initial ray. Well, this extraordinary beam coming like this, then going into this twisted crystal, well, what happens to it is it, in fact, divides this beam into two separate beams, one that acts like an ordinary beam and one that acts like an extraordinary beam. Okay, and so some of these are going to be coming out in the direction of the diagonal one way, and the other ones are going to be coming out in the direction of the diagonal the other way. So by twisting the crystal, you can further subdivide this into two beams like this. So we're going to come back to this a bit later on when we study the work of John Tyndall and his work on polarization. But it's interesting that Newton here is trying to understand the behavior of light in terms of its orientation or its sidedness. And the way that he does this is by conceiving of light as tiny particles that have these properties of the sidedness of these particles or orientation of these particles. And he, in fact, calls it a polarity or a polarization. And Newton is really onto something here. He's onto something that Huygens was not able to explain. Remember, Huygens has this wave theory of light where he's comparing it to a pressure wave or a sound wave. And Newton here is emphasizing that there's a sidedness to it, a polarity to it that cannot be accounted for by Huygens' theory. Okay, so again, we'll come back to this later. So if you look at page 213, the bottom on the query number 27, remember Newton is structuring this in terms of queries or questions and then answers. He says, query 27, are not all hypotheses erroneous, which have hitherto, that means up until now, hitherto been invented for explaining the phenomena of light by new modifications of the rays? For those phenomena depend not upon new modifications, as has been supposed up until Newton, but upon the original and unchangeable properties of the light rays. So what is he getting at? He's saying here that other scientists were imagining that when the light hits this Iceland spar or crystal, it acquires some property. There's a new modification or a new property that it acquires as a result of hitting this Iceland spar. And what Newton is emphasizing is it's not some new property. The light itself has a property, this polarity or sidedness that the Iceland spar simply acts upon in filtering it and breaking it up into two different beams. So it's an old or original and unchangeable property of the rays. Okay. Now, what does Newton do from here on out? Well, what he's going to do is he's going to offer a criticism of Huygens' theory of light. This is in query number 28 at the bottom of page 213. He's going to criticize Huygens' wave theory of light, and then he's going to embark on quite a bit of speculation about the nature of light. And Newton covers a lot of material in this chapter. There's a lot of speculation. I'm not going to be able to go through all of this in detail, but I'm going to hit what I think are some interesting points. I'd highly recommend you to read this. It's a little bit of a hard read, but there's a lot of interesting stuff in here. So why don't you look at the bottom of page 213 and the top of page 214, where he says, are not all hypotheses erroneous? Okay, so he's asking a rhetorical question. aren't the people who think differently than I do erroneous? Are not all hypotheses erroneous, in which light is supposed to consist in pressure, or motion propagated through a fluid medium? So he has here in mind directly as a target Huygens' wave theory of light, where you might recall Huygens is imagining light to be pressure or vibrations inside of a fluid medium, this ether that fills all of space. So Newton here is poking at this, saying, isn't everybody completely wrong who thinks that light consists of pressures or motions propagating through some ethereal medium? And then what he does is he goes on to explain why he thinks this is wrong. And the first thing he does, and this is on page 214 in this long paragraph, he talks about how if you think about how pressure spreads through a medium, it spreads uniformly throughout a medium. And for those of you who have taken my Physics 151-201 class on space, time, and motion, we spent a little bit of time studying the work of Blaise Pascal. This is a little bit of a digression here, but this is relevant. So Blaise Pascal, who was a French scientist in about the 1620s, a little bit before Newton, he did a careful study of the way that pressure is transmitted through a fluid. So if you have a fluid-filled chamber with a hole on one side, and you apply pressure using a piston to this hole, the pressure is immediately transmitted throughout the entire medium, and that pressure is exerted on all the walls of this chamber. So if I were to draw a little diagram right here, imagine that we had a chamber with a couple of holes in the sides like this. This is just a two-dimensional drawing. And you were to imagine that you put a piston, a tight-fitting piston right here, and there was another piston over here, and this entire chamber was filled with fluid, like water, let's say. It doesn't matter what kind of fluid, but if there's a fluid-filled chamber, and you apply a force right here, so there's some pressure exerted on this, and this pressure, according to Pascal's principle, which Newton no doubt has in mind here, Pascal's principle, this fluid pressure is spread throughout this entire chamber, and there's a pressure exerted on all of the walls of this chamber and on this piston, which will try to drive that piston forward. So Newton is referring to this. He's saying, if we're thinking about light in this way, it seems that light would immediately fill an entire chamber. And this isn't what light seems to do. Light seems to travel in straight lines. It seems to travel, if you open up a hole in the wall, there's a beam of light that comes through this hole. It doesn't immediately fill the entire room. There's actually a ray of light. So Newton here is appealing to common sense about how light behaves, and saying if we're going to think about it like a pressure transmitted through a fluid medium, we're going to run into these kinds of problems. That's what he's talking about on this long paragraph on page 214. Newton also criticizes Huygens on the last full paragraph on page 214, where he says even Huygens, when he's trying to explain the birefringence of Iceland's spar, Huygens, because he doesn't believe in Newton's particle theory of light, he believes that light is a pressure. In order to account for this birefringence, or the bending of light into two separate beams, Huygens has to appeal to two separate different kinds of fluid media, or two different kinds of ether. And this complicates Huygens' theory in a way that Newton thinks is not aesthetically appealing or not appropriate. So he's trying to here criticize Huygens' wave theory of light without mentioning Huygens by name. In fact, actually, he does mention Huygens by name. He says, to explain the unusual refraction of island crystal by pressure or motion propagated has not hitherto been attempted to my knowledge except by Huygens, who for that end supposed two several vibrating mediums within that crystal. But when he tried the refractions in two successive pieces of that crystal and found them such as mentioned above, he confessed himself at a loss for explaining them. So even Huygens was not satisfied with his own explanation. Okay, and then on the next page, there's a long digression about how if one believes that light is a wave traveling through some medium, that implies there must be some medium filling space, and this medium should have other effects that we do not in fact observe. So he talks here about drag in particular. There's a long digression on page 215 where he talks about the effect of fluid on bodies that are attempting to move through it. So in particular, he mentions that if you have some sphere like a ball that is falling through water or air or liquid mercury or some other kind of material, that medium will exert a drag force on it. And he talks about the kinds of drag force that are exhibited that arise because of the inertia of the fluid. This would be, by the way, this is called turbulent drag. That goes as a square of the velocity of the object moving through the fluid. And he also talks about the kind of drag that arises because of the tenacity or the stickiness of the fluid. That would be laminar or viscous drag that is proportional to the speed of the object moving through it. There's a lot of material in here, a lot of interesting points that he's making, but he's trying to calculate the effect that this ether should have on bodies that are moving through it if the ether in fact exists. And he argues that there should be some appreciable effects. This ether should exert some kind of drag on objects moving through it. Since we don't see this drag acting on fluid, on objects moving through the ether, that implies that perhaps the ether is not in fact there. So this is at the bottom of page 216. I'd like to just point out a couple of paragraphs here. He says, or a couple of sentences at the end of the last full paragraph on page 216. He says, a dense fluid can be of no use for explaining the phenomena of nature, the motions of the planets and comets being better explained without it. So he's saying if you look at the motion of Mercury or Venus or comets, whatnot, moving through space, if space was full of this ether, they should exert a drag on those planets, and those planets should be slowing down over time. It might be a small effect, but it should be there. And for as long as anyone has cared to observe the planets, they've always been orbiting with the same speed in the same direction, at least according to the records that Newton has accessible to himself. Since no one notices the periods of the orbits of the planets getting longer because of drag, therefore that's evidence against the existence of some medium filling space. And then he goes on to say, it serves only to disturb, this ether would serve only to disturb and retard the motion of these great bodies and make the frame of nature languish. So nature would sort of get more sluggish, or things would slow down over time, which they don't. And in the pores of bodies, the ether serves only to stop the vibrating motions of their parts, wherein their heat and activity consists. So if we're thinking of heat, as Newton is, as vibrations of the atoms that comprise bodies, then ether would would exert a drag on those vibrations, and they would actually lose their heat over time. And as it is, and here's his conclusion, he says, the ether is of no use and hinders the operations of nature and makes her languish, so there is no evidence for its existence, and therefore it ought to be rejected. And if it be rejected, the hypotheses that light consists in the pression or motion propagated through such a medium are rejected with it. So here is the sum of Newton's argument. If we haven't observed the ether, and if it doesn't really serve any valid purpose, and if it only causes problems, we should just reject altogether this notion of ether. And then what he does next at the bottom of page 216 is he cites the work of the ancients. So he mentions here the ancients, such as, he doesn't mention Democritus by name, but that's what he's talking about here. He says, the philosophers of Greece and Phoenicia, who made a vacuum and atoms and the gravity of atoms the first principles of their philosophy. So according to people like Democritus, nature, we see things around us like desks and chairs and tables and people and animals, and they look like desks and chairs and people and tables and animals, but really they're just comprised of atoms that are separated by void or vacuum. And that seems to be the approach that Newton is endorsing here. And then he goes on to say that later philosophers, when they were looking at things like gravity, they supposed that gravity cannot actually be a material cause. It can't be a material in and of itself. Rather, there must be some immaterial cause of gravity. This is on the top of page 217. Gravity is not a material object. It's a power that material objects have. And then he starts asking questions. What is the source of this power? Where does this power come from? And pretty soon, if you ask these sorts of questions, one arrives at a first cause. He says scientists come up with or feign hypotheses to deduce cause from effect until we come to the very first cause, which certainly is not mechanical, and not only to unfold the mechanism of the world, but chiefly to resolve these and such like questions. So if one asks, why do things behave the way they do? Eventually one must ask questions that have as an answer an immaterial cause. And now this is, by the way, the topic of what came to be known as natural theology. How does one arrive at the idea of the existence of God from purely from looking at nature, without appealing to any kind of scriptural or theological sources? By looking at nature, can one infer the existence of a God or a God? So he asks some interesting rhetorical questions. He says, whence is it that nature doeth nothing in vain? And whence arises, from where arises all that order and beauty which we see in the world? To what end are comets? And whence is it that planets move all one in the same way, in orbs concentric? So why is it that all the planets happen to be orbiting the sun in the same direction? It seems too unlikely to have been happening by chance. And he says, while comets move all manner of ways in orbs very eccentric. And what hinders the fixed stars from falling upon one another? So why is it if that all the stars are attracting one another via gravity, as Newton had explained in his Principia, why didn't they fall in on each other by now? What's holding them up? How come the bodies of animals to be contrived with so much art? And for what ends were there several parts? Animals seem to be designed, he says here, and they seem to be designed with a purpose. Was the eye contrived without skill in optics, and the ear without knowledge of sounds? How do the motions of the body follow from the will? And whence is the instinct in animals? And so he's asking these questions about, by looking at nature, nature seems to point to something beyond it. And this is precisely what Newton is arguing here. And he does this more explicitly later on in one of his later chapters. He makes an explicit natural theological claim that by looking at nature, one can deduce the existence, using reason, of God or a God. Okay, so tell you what, I'm going to stop there. I'll probably make a few more comments about Newton's, this chapter from Newton's Optics during my next lecture. And then after we finish up Newton, we will probably move on to the work of Thomas Young.